Hello and welcome to Honors Function. This is the last lecture of the series on inverse function. This is also the last lecture of this unit number 2 on functions. So in this lecture we're going to be doing a couple of things. First, we're going to be taking a look at the relation between the graph of a function and the graph of its inverse. We've already stated the result. We're going to take a closer look at it. And second, we are going to see what to do when the function is not one-to-one, when it doesn't have an inverse. Can we do something to make it one-to-one by working on the domain? And finally, we're going to be seeing how the calculator can help us figure out if we have two inverse functions of each other. Okay? So let's start with the first point to take a closer look at the relation between the graph of a function and the graph of its inverse. So suppose you look at the function, the graph of a function like this one, for example. Now this is a one-to-one function, right? Because it passes the horizontal line test. If it's one-to-one, therefore it has an inverse, okay? Now suppose you have a point right here that I'm going to call AB. We know how to find a point on the graph of its inverse. You need to use a line y equals x, right here, y equals x, right? And this A and this B, you have to send them. A has to go on the y-axis and B on the x-axis, right? Here's A, here's B. How do you send this A on the y-axis? Use the line y equals x. So you go to the line and then you go to the y-axis right here. Here's A on the y-axis. How do you send this B on the x-axis? Okay, well, you go to the line y equals x and you go right here, right here. That's B. And so now I have the point BA right here, BA. The relation we already established that is symmetrical with respect to the line y equals x, and this is one point on the graph of the inverse function. This is a function, and this is one point on the graph of the inverse function. How do you find them all? Well, you gotta take the symmetric with respect to all the points. So for example, this point right here, 0 something, right? Well, it's gonna find itself somewhere there, right? I'm taking the symmetric. So basically I'm gonna eyeball it. We're gonna have to do a better drawing. It looks like it looks like this line is like an asymptote. I'm not sure. So I'm gonna eyeball the mirror image. It looks like it goes like that. You see, symmetrical with respect to the line. This is a mirror image, same distance on the other side. Okay? So this is what you need to do when you want to graph the inverse function. This would be the graph of y equals f minus 1 of x. You have flipped all your point on the graph of the function f. Okay, so let's go over the first example. So I'm going to do example 1 and you're going to tackle example 2. So I'm giving you a function and you see that it does passes the horizontal line test, right? Every horizontal line will cut the function, the graph of the function, in only one point. Therefore, this function is one-to-one. It has an inverse. Okay. I'm also giving you the graph of equation y equals x. You need to do the mirror image of the red graph with respect to this line. Okay? So how do we do it? Well, first of all, I'm spotting these 2 points. They are on the mirror. They are not going to move. Okay, so my inverse function has to go through these 2 points. Second, I'm spotting this one right here. This is -1, 0. It's going to go to 0, -1. Sorry about that. 0, -1 right here. And then this little one right there is going to go right here. So, I mean, this is not helping very much. These points are really close together. Okay, then what do we need to do? Okay, look, it seems to me that this line, maybe right here, it seems to me that this line is a vertical asymptote. I haven't yet talked about vertical asymptotes, but I know you've covered that last year. It's a line through which the function is getting close. It seems to me that it's a vertical asymptote, right? So this is a line x equals 3. And so I should have a horizontal asymptote at y equals 3. Y equals x. You flip x and y. So I should have a horizontal asymptote right here. And look at this horizontal asymptote right here. It looks like I have a horizontal asymptote, right? The red graph keeps on going this way, right there. And this is y equals 1. Therefore, I'm expecting x equals 1. So I have this line as a horizontal asymptote on my inverse, and x equals 1 as a vertical asymptote of my inverse. Why x equals 1? Because it comes from y equals 1, which is a horizontal asymptote of f, right? And x equals 3 is a vertical asymptote of f. Therefore, x equals 3 becomes y equals 3, and that should be a horizontal asymptote of f inverse. And y equals 1 becomes x equals 1, and x equals 1 should be a vertical asymptote of f inverse. Okay, you have to flip them both. So let's try to take a stab at this graph right here. So I would say maybe something like this, and then this way right here for this branch. Sorry, a mistake on this side. It's going much further. It's going here. Too many lines here, I guess, right? Like that for the first branch. And for the second one, so don't forget you have these 3 points right here. Something maybe like this. Like that, okay? And the red, now let me erase all my stuff right here. Let me erase this. Let me erase all these vertical and horizontal asymptotes. So we're going to try to see clearly that the red graph and the blue graph are symmetrical, mirror image of each other with respect to this line. Okay? If you fold the graph along this line, this would go on top of this, while this would go on top of this, and this would go on top of this, while this would go on top of that. Right here. Okay? I know it's a little bit messed up because of the graph. Example 2 is for you. Let's move on. So we worked on function given numerically before. Here are some examples of 2 functions given numerically. And I am also talking about f inverse and g inverse. I hope I haven't made a mistake and I can talk about f inverse, right? Let me see. 3, 2, 0, negative 1, negative 2, negative 5, 1, negative 1. I haven't repeated a single term here, right? Therefore, the inverse relation is an inverse function. How about g? 0, negative 2, negative 4, 1, negative 3, 3, negative 1, 7. Okay, the inverse relation also here is an inverse function, so I am entitled to talk about these 2 functions. Okay? Alright, so what is, for example, f of g inverse at negative 4? So you know what it means. It means f of g inverse at negative 4. So g inverse at negative 4, okay, you look at g, it goes from I don't know what to 4, negative 4 right here, that's g, and g inverse of negative 4 is going to go back to I don't know what. So this is an output of g, right? Output of g. It's an input of g minus 1, it's an output of g. Therefore, I have to look at the column of output. Negative 4 is right here. G inverse of negative 4 is 0. So this is f of 0, and f of 0 is negative 2. Right here. Okay? Yes? Clear? Let me do another one and you're going to do the other. These are not difficult. I expect that to be pretty okay. Here I'll do... I'm going to do number 6 and I'm going to let you do the other 4. Okay? So what do you do right here? You have to find g inverse of f of g at negative 2. Alright, g at negative 2, so this is g inverse equals g inverse of f of, what is g at negative 2? It is negative 3. What is f of negative 3? It is 2. So I have g inverse of 2, and g inverse of 2, I'm going to look at the column of my g's right here. and I don't have any output that is equal to 2. Therefore, represent compute the indicator value if they exist. Therefore, dne does not exist. Okay, not enough information to answer this question. All right, so question mark right here. Okay, all right, do the other 4, please. Okay, in this example, we are dealing with a quadratic function. I need to quickly check out its graph. So let me check out its graph. That's easy. I'm going to complete my square. X minus 2 squared minus 4 plus 5. So it is f of x equals x minus 2 squared plus 1. All right. So let me quickly sketch the graph, right? I know how to do that. I'm going to 2, and my y, the y value of the vertex is 1, so, and it's shaped like x squared, so something like this, right? Now, this graph does not, the function doesn't pass the horizontal line test, of course, right? It doesn't pass the horizontal line test. So this function does not have an inverse. There is a way, though, to restrict the domain. Here, the domain is all real number, right? There's no problem. This function is defined for every real number. I can restrict my domain, though, and I see that, I don't have to graph anything, I see that from my vertex. The vertex is 2, 1. Therefore, I could restrict the domain either from negative infinity to 2, right here, or I can restrict it from 2 to infinity. What does it mean? That means either I'm looking at this part of the graph, and you have to agree with me, this passes the horizontal line test. Or I'm looking at the other side of the graph. I'm looking at, right here, I'm looking at this branch right there. Okay, from 2, and this is 1 right here. Okay, so either I'm restricting this way, my domain, or I'm restricting like that. And these two will pass the horizontal line test, and therefore they have an inverse function, right? Okay, now you're going to be doing the next example. It's quite important, okay? But I'm talking about this function right here, the one I just went over in example number 9. And I want you to restrict it with the domain that includes infinity. So basically, we are looking at this function right here. So here, let me write it for you. It's a function that goes from 2 to infinity into 1 infinity, okay? And I want you to find the inverse of this function. I want you to find the expression of the inverse of this function. So again, the function is, and actually it may not be a bad idea to, I don't know, maybe you want to look at this right here, this expression, or maybe you want to look at this expression. I don't know, whatever suits your fancy right here. But this is what you need to do, right? I think it's plus 5, right? Yeah, plus 5. You need to find f minus 1 at x. Okay, you need to find the inverse of f at x right here. Okay, finally, last part of this medley of topics about inverse function. Let me go over the last example. It is a calculator problem. How can you check with the calculator if you have the right graph for the inverse function? So let me go to example 11. Okay, example 11 has to do with an example we did before. Example 2 in notes, actually, this is 31, okay? So in example 2, and I think I may have done it, or maybe you, I don't know. In example 2 in note 31, the inverse function that we believe we have is 2x plus 3 over 2 minus x. How can I check with my calculator if I have the right function or not? Well, that's pretty simple, right? What happens if you plug this into f minus 1? Well, you know what you're supposed to find. You're supposed to find x. Likewise, if you plug this into that, okay, if you plug f of x into f inverse, you're supposed to find x. So how can you check with a calculator? Very easy. I'm going to plug f into y1. I'm going to plug f inverse into y2. And I'm going to do y2 of y1 of x. And also y1 of y2 of x, right? Actually, I just need to enter that in my calculator. I'll enter that in y3. and I'll enter this one in y4. I'm also going to show you how not to graph everything to see clearly what you're doing. And if you're right, you know what y equals x looks like, right? It looks like a line like this. Now, it's going to be a line like that, and maybe it won't be everywhere. We'll see. We'll see. Okay, ready? Let's take the calculator then. Okay, here's a calculator. So the first thing I want to do, I want to go in my y equals menu, and I want to enter my two function. The first one given to me, which is f of x, which is 2x minus 3 divided by, and at the bottom I have x plus 2. Here we go. That's the first one. The second one is the one that I believe is the inverse, the one that I think is the inverse. So I have, I believe, 2x plus 3, 2x plus 3 divided by 2 minus x, 2 minus x. Okay, I believe these two functions are inverse of each other. And I'm going to check that graphically, right? So the first thing I'm going to do is, I do not want to graph this function. I do not want to graph this function. So look what I'm going to do. I'm going to go on top of my equality right here, and I'm going to push enter. And you see, it's no longer highlighted. The equality is no longer highlighted. Look at this equality right here. It is highlighted, right? So I'm going to go on top of it, and I'm going to push enter. It's no longer highlighted. My function will not graph it. In y3, I'm going to enter y2 of y1. So I think we went over that. Yeah, we did when we did composition of functions. So vars right here, vars, y vars right here, function, and let's do y2 of, so parenthesis, and then y1, vars, y vars, function, y1. Right here, y2 of y1, and in the next one, I will want y1 of y2. So vars, y vars, function, y1 of vars, y vars, function, y2, right here. All right. Let me not highlight, let me not graph y4 for the moment. So I'm not going to graph y4. I'm going to do a zoom standard. And let's see what we have. Oh, look at this. Beautiful. It takes a while to graph because actually the function has to compute a lot of things, right? It goes through y1, it goes through y2, and it does y1 of y2. If you graph y equals x, it will be very fast. So, great. That works. Let me check the other one. Well, actually, I'm pretty sure I'm on the right track right here. Okay. Let me check the other one. So let me not graph this one, and let me graph this one right here. So you push enter. Now it's highlighted. Let's graph it. And our different color. Nice. I like this color. Okay, and you can see that it works too. Alright guys, this is the end of the video. Thank you for watching.